James Webb just detected a gas that shouldn't be there. 124 light-years from the chair you are sitting in, there is a planet that may have no ground at all. No coastline, no mountains, no solid surface anywhere on it. Just an ocean, wrapped in a hydrogen sky, circling a small red star so closely that its entire year lasts 33 days. That would already be strange enough. But in April of 2025, a team using the James Webb Space Telescope reported something else in that sky. A faint chemical fingerprint. A sulfur gas called dimethyl sulfide. On Earth, almost every molecule of that gas comes from living things. Marine plankton make it. It is part of the smell you notice at the seaside. It has no significant non-biological source on our planet. And nobody expected K2-18b to be doing anything like this. Stick around, because I'm about to walk you through what scientists actually just confirmed about K2-18b, and, just as importantly, what they immediately unconfirmed. And, hit subscribe now, because this channel breaks down real space discoveries without the exaggeration. Let's go back to where this story actually begins. The story does not begin with James Webb. It begins with a telescope that was already old, and a job that was already boring. In 2015, astronomers working with data from NASA's Kepler Space Telescope confirmed a new planet. Kepler's primary mission had ended. 2 of its 4 reaction wheels had failed, so it could no longer hold a steady stare. Engineers salvaged it by balancing the spacecraft against the pressure of sunlight itself, and that patched-together second life was called K2. The 18th star system cataloged in that extended mission was a small red dwarf in the constellation Leo. Its first confirmed planet got the plainest possible name, K2-18b. At first, it looked unremarkable, about 2.6 times the width of Earth, roughly 8.6 times Earth's mass, orbiting once every 33 days. Understand what that combination means. A planet 2.6 times Earth's width, but only 8.6 times its mass, is not dense enough to be rock all the way through. Squeeze that much rock into that much volume and the numbers do not work. Something light has to be filling the difference. Water, or hydrogen, or both. So before anyone had looked at the atmosphere, the bulk density was already telling you the planet was not a bigger Earth. It was something else. Something we have no example of anywhere in our own solar system. Around a star like our Sun, a 33-day orbit would be a furnace. But K2-18 is not like our Sun. It is an M-dwarf, smaller, cooler, dimmer. So that tight, fast orbit places the planet inside the habitable zone, the band where liquid water could, in principle, exist. That single fact moved it from a catalog entry to a target. And it is worth being precise about what habitable zone actually means, because the phrase does more work in headlines than it does in science. It does not mean habitable. It means the planet receives roughly the amount of starlight that would allow liquid water to sit on a surface, if the planet had a surface, and if it had the right atmospheric pressure, and if nothing else went wrong. 3 enormous ifs. The habitable zone is a lighting condition, not a verdict. K2-18b receives roughly the same amount of energy from its star that Earth receives from the Sun. That is the entire claim. It says nothing about what is underneath. The next step was archival work, and archival work is tedious. Between 2016 and 2017, the Hubble Space Telescope watched K2-18b pass in front of its star a handful of times. 8 transits, recorded and stored. Nobody had squeezed them properly. In 2019, 2 separate teams did. One was led by Angelos Tsiaras at University College London, the other by Bjorn Benneke at the Université de Montréal. They worked independently. They used different methods. They were looking at the same handful of old observations. Both found the same thing: water vapor. The announcements landed within days of each other. And for a moment, the headlines wrote themselves. First habitable zone planet, with water in its atmosphere. That was the turning point, but not for the reason most people assumed. Because the honest reading of that result was much narrower. Hubble's instrument covered a limited slice of infrared light. In that slice, water vapor and methane produce features that overlap. Some researchers argued the signal could have been methane instead. Hubble simply could not tell them apart. The data had reached its ceiling, not the scientists, the hardware. So K2-18b went onto a list of targets waiting for a telescope that did not exist yet. That telescope launched on Christmas Day, 2021. Here is the part that sounds impossible until you break it into steps. We are not photographing this planet. We have never seen it. There is no image. There never will be, not with current technology. What we have is a shadow. K2-18b passes between us and its star once every 33 days. When it does, it blocks a tiny fraction of that star's light. For K2-18b, that dip is roughly 1/3%. The star gets very slightly dimmer, for a few hours, then returns to normal. Now follow the chain. Starlight is not one thing. It is every wavelength at once. Split it apart and you get a spectrum. During a transit, some of that starlight does not hit the planet. It grazes the edge. It passes through the thin ring of atmosphere at the planet's rim, before continuing towards us. Molecules in that atmosphere absorb light, but they do not absorb it evenly. Each molecule absorbs at its own specific set of wavelengths, like a barcode. Methane has one barcode, carbon dioxide has another, dimethyl sulfide has another, so at the wavelengths a molecule absorbs, the planet effectively looks slightly bigger. It blocks slightly more light. The dip gets slightly deeper. Measure the depth of that dip at hundreds of wavelengths at once, and you get a curve. Bumps in that curve are molecules. There is one more piece of luck involved, and it is worth naming. How far an atmosphere puffs out from a planet depends on how heavy the gas is. Heavy molecules sit low, light molecules spread out. Hydrogen is the lightest gas there is, so a hydrogen-dominated atmosphere extends much further from the planet than a nitrogen one like Earth's. A puffier atmosphere means a bigger ring of gas for starlight to pass through. A bigger ring means a stronger signal. That is precisely why K2-18b is measurable at all, and why an Earth twin around a Sun-like star is still, today, out of reach. The atmosphere we might actually be able to read is not the one most like our own. It is the one least like it. That is transmission spectroscopy. It is the entire foundation of atmospheric science for exoplanets, and it rests on one uncomfortable fact. The bumps are measured in parts per million. Think about that scale for a second. The planet blocks about 1/3% of the light. The chemical signal sits on top of that as a variation of a few tens of parts per million. You are trying to detect a change of roughly 1 part in 50,000 in the brightness of a dim red star 124 light-years away. That is not like finding a needle in a haystack. It is like weighing a haystack twice, 1 hour apart, and trying to work out whether a single needle was added. Which brings us to why this took 30 years of instrument development. Everything about this measurement is working against you. Start with the target. K2-18 is a red dwarf, and red dwarfs are not calm. They have star spots. They have bright regions called faculae. As the star rotates, those patches move across its face, and the star's brightness changes on its own, with no planet involved at all. That matters, because a star spot can imprint a false bump into your spectrum, a signal that looks chemical but is stellar. Researchers call it contamination, and for M-dwarf planets, it is the permanent background problem. There is no way to switch it off. You can only model it and accept the uncertainty it leaves behind. Now add the clock. The planet transits once every 33 days. If you miss a window, the next one is a month away. James Webb is one of the most oversubscribed instruments in the history of science. Telescope time is allocated in hours, argued over by committee, and every hour you take is an hour some other team does not get. So you cannot simply keep observing until the answer is obvious. You get a handful of transits, maybe a few more, if the result is interesting enough to justify a follow-up proposal. Now add distance. 124 light-years. The light arriving at Webb's mirror right now left that system around the year 1902. Nothing about this can be checked in person, ever. No probe will go. At the fastest speed any human object has reached, the journey would take longer than recorded human history. Add the instrument itself. Webb's detectors are extraordinary, but they are physical objects, and physical objects drift. Temperatures shift by fractions of a degree. Detector pixels respond slightly differently over the course of a long observation. There is a well-documented effect where a detector's response changes as it settles into a stare, and it does so on roughly the same timescale as a planetary transit. That is a genuinely dangerous coincidence. The thing you are trying to measure and one of the things corrupting your measurement unfold over the same few hours. Teams correct for it. Different teams correct for it differently. And those different correction choices are one of the main reasons two groups can pull the same raw file and produce different curves. And add the last constraint, the one that decides everything else: statistics. In physics, confidence is measured in sigma. Sigma tells you how likely it is that random noise alone could have produced a bump that big. 3 sigma means roughly a 1 in 300 chance of it being a fluke. 5 sigma, the threshold the field uses for a genuine discovery, means roughly 1 in 3.5 million. That gap sounds small. It is not. The history of particle physics and astronomy is full of 3 sigma results that evaporated when more data arrived. 3 sigma is not a discovery. 3 sigma is a reason to look again. Hold on to that number. 3 sigma. It is about to become the whole story. September 2023. The atmosphere finally answers. James Webb turned to K2-18b in 2023, using its near-infrared instruments, NIRIS and NIR-SPEC, across a wavelength range Hubble could never reach. A team led by Niku Madhusudan at the University of Cambridge published the result. They found methane, they found carbon dioxide, both at high confidence. For the first time, carbon-bearing molecules had been identified in the atmosphere of a habitable zone planet of this size. But the finding that made theorists sit up was an absence. There was no ammonia. In a thick hydrogen atmosphere over a rocky or gaseous interior, ammonia should be there. Nitrogen and hydrogen combine readily under those conditions. Its absence needs explaining. One explanation is a liquid water ocean. Ammonia dissolves into water very efficiently. Give the planet a global ocean beneath a hydrogen sky, and the ammonia gets scrubbed out of the air. Madhusudan's group had already given this hypothetical class of world a name: Haitian, hydrogen atmosphere, ocean surface. If K2-18b is Haitian, the ocean underneath that sky could be planet-wide. A single body of water with no shore anywhere on it. A surface roughly 7 times the total surface area of Earth, with nothing to interrupt it. And in the same 2023 paper, buried in the analysis, there was a weak hint of something else, a possible feature consistent with dimethyl sulfide. The authors were explicit that it was tentative and required validation. That hint is what earned K2-18b more telescope time. In practice, that single tentative line in a 2023 paper is the reason this entire story exists. A weak feature, flagged honestly, was enough to justify pointing the most expensive telescope ever built back at the same planet with a different instrument. That is how the process is supposed to work. A hint buys you a second look, nothing more. What remains unexplained, whether that ocean exists at all. A spectrum tells you what is in the upper atmosphere. It does not tell you what is underneath it. April 2025. A different instrument, a different color of light mints. The follow-up used MIRI, Webb's mid-infrared instrument. Completely separate detector, completely separate wavelength range, from the 2023 observations, out past 6 microns. That independence is the point. If a signal appears in one instrument and then again in a different instrument at different wavelengths, it is much harder to blame on a quirk of the hardware. In April 2025, Madhusudan's team published the MIRI result in the Astrophysical Journal Letters. They reported a spectral feature best fit by dimethyl sulfide, or by a close chemical relative called dimethyl disulfide, or by some mixture of the two. The statistical significance they reported was about 3 sigma. Now, why does this molecule matter more than methane or carbon dioxide? Because of what makes it. On Earth, dimethyl sulfide is produced almost entirely by biology. Marine phytoplankton generate a precursor compound. That compound breaks down, the gas escapes into the air. It drifts up, helps seed cloud droplets, and it is a genuine part of Earth's climate machinery. It is not a trace curiosity. It is one of the largest natural sources of sulfur, moving from the ocean into the atmosphere of this planet. And in Earth's atmosphere, it does not last. Sunlight destroys it within about a day, which means that if you detect it, something must be making it continuously, right now. That is why it sits on the biosignature candidate lists. Not because it is exotic, because on our one-worked example, it is manufactured by life and replenished by life. The abundance the Cambridge team's models preferred for K2-18b was not a trace. Their fits pointed to concentrations thousands of times higher than Earth's atmospheric levels. To their credit, the team said the correct thing publicly and immediately. This is not a detection of life. This is a possible detection of a molecule that, on Earth, is associated with life. 3 sigma, not 5. What remains unexplained? Everything downstream of that sentence. The reanalysis. When 3 sigma becomes 0 head. Here is the part the headlines mostly skipped. Within weeks, other groups pulled the same public data and ran their own analyses. This is normal. This is the system functioning exactly as designed. The results were not kind. One reanalysis, led by Jake Taylor at Oxford, applied a deliberately assumption-light method, one that does not start by asking how much of molecule X fits here, but simply asks whether the spectrum contains any structure at all beyond a straight line. It found essentially none. The data were consistent with a flat line. Other independent teams, including groups led by Raphael Luque at the University of Chicago and researchers working with Luis Wellbanks, combined the 2023 and 2025 observations and reran the fits. Their conclusion was consistent. Dimethyl sulfide was not statistically preferred. Several teams found the significance dropping towards 1 sigma or lower, which is another way of saying no signal. They also found something more awkward. Dozens of different molecules could fit that same bump about equally well. Ethane, various nitrogen compounds. Different combinations produced nearly identical curves. That problem has a name: degeneracy. When your signal is at the edge of your noise, many different physical stories produce the same measurement, and the data cannot arbitrate between them. And there is a subtler issue underneath it, which is about how the question gets asked. If you build a model that already includes dimethyl sulfide, and then ask the data how much of it is present, the fitting process will hand you a number. It almost always will. That number is not a detection. It is an answer to a question you supplied. Ask instead whether the data contain any structure at all, without telling the software what to look for, and you get a different kind of answer. That is what the Oxford reanalysis did. And the answer it got was, not much. Both approaches are legitimate. They are asking different questions. But they do not carry the same evidential weight, and the distinction between them almost never survives the journey into a headline. None of this makes the original team wrong to publish. They reported a 3 sigma feature, labeled it as a 3 sigma feature, and said out loud that it needed confirmation. That is the correct behavior. The distortion happened downstream. Think about what 3 sigma actually looked like here. 1 in 300 odds of a fluke. Astronomers run thousands of these fits every year across hundreds of targets. At 1 in 300 odds, coincidences are not rare events. They are expected events. What remains unexplained, whether the feature is real and weak or simply not there, both are still live options, and the current data cannot separate them. The other problem, the gas is not exclusive. Set the statistics aside for a moment. Suppose the molecule is genuinely there. That still would not mean life. In 2025, researchers analyzing data from the European Space Agency's Rosetta mission reported dimethyl sulfide in the material streaming off Comet 67P, Churyumov-Gerasimenko. Rosetta's Rosina instrument sampled that gas directly, from a few kilometers away, and comets are not biological. The same molecule has also been identified in cold interstellar gas clouds, regions of space with no planets, no oceans, and no plausible biology. So the premise underneath the whole story has a crack in it. Dimethyl sulfide can be produced without life. We have now measured it being produced without life, twice, in 2 completely different non-living environments. That does not make the K2-18b result uninteresting. It changes what the result could ever mean. Even a clean 5 sigma detection would not be an announcement of life. It would be an announcement of a molecule that requires an explanation. And think about where the comet detection came from. Rosetta spent 2 years flying alongside 67P, close enough to taste the gas coming off the surface directly. That is about as clean a measurement as it is possible to make in planetary science. No starlight, no modeling of a distant atmosphere, a physical instrument, sampling physical molecules. That measurement is far more certain than anything we have from K2-18b. And what it tells us is that the molecule we were treating as a signature of life is also produced by a lump of ice and dust in our own solar system, with no biology involved anywhere. Compare it to how we treat methane on Mars. Detected, argued over for 2 decades, and still unresolved between geological and biological sources, on a world we have rovers driving across. K2-18b is 124 light-years away. What remains unexplained? The abiotic production rates. Nobody yet knows how much of this gas a lifeless, hydrogen-rich atmosphere can make on its own. And the planet itself might not be what we think be. There is one more layer, and it undercuts the ocean. Other researchers at Cambridge, including a group led by Oliver Shortall, published an alternative model. In it, K2-18b is not a Hycean world at all. It is a smaller, hotter object with a magma ocean, molten rock, not water, beneath its hydrogen envelope. That model also removes ammonia from the atmosphere. Molten rock dissolves nitrogen. You get the same observed absence, with no habitable surface anywhere. Other groups have argued the planet is simply a mini Neptune, a deep hydrogen envelope with crushing pressures and temperatures far below, and no surface in any meaningful sense at all. All three models, Hycean ocean, magma ocean, mini Neptune, are broadly compatible with the spectrum we currently have. At 8.6 Earth masses and 2.6 Earth radii, K2-18b sits in a size range that has no representative in our solar system. There is nothing between Earth and Neptune here. We have no local example to calibrate against. Subneptunes appear to be the most common type of planet in the galaxy, and we understand them the least. What remains unexplained? What is underneath? Not the chemistry, the structure of the planet itself. What would actually count sub? So ask the harder question. What would it take? Not a bump. Not one molecule. Chemists who work on biosignatures have largely abandoned the idea that any single gas can be proof of anything. What they look for instead is disequilibrium, an atmosphere containing gases that should react with each other and destroy each other, present together anyway, in quantities that require constant resupply. Earth's atmosphere is the example. Oxygen and methane should not coexist. They react. Left alone, the methane disappears within about a decade. The fact that both are present, permanently, means something is pumping them out faster than chemistry can remove them. That is what a biosignature actually looks like. Not a fingerprint. A budget that does not balance. For K2-18b, you would need to detect dimethyl sulfide at 5 sigma in more than one instrument, confirmed by more than one independent team. Then you would need to rule out every non-living process that could make it in a hydrogen atmosphere, and the modeling required to do that has barely started. Then you would need supporting molecules that fit a coherent biological story, and no plausible geological one. We are at step 0 of that list, not step 1, and here is the thing worth defending. The reanalyses that knock the signal down are not the system failing, they are the system working. A result was published, the data were made public, other groups checked it, and the claim weakened. That entire sequence took a matter of weeks. What remains unexplained? How much of the observed spectrum is planet, how much is star, and how much is detector? Until that is separated cleanly, nothing above it can be trusted. So how does this get settled? More time on the same telescope. Madhusudan's team has estimated that on the order of another day of Webb observations, a handful more of those 33-day transit windows could push the significance either to 5 sigma or to nothing. Additional observations have already been carried out and analyzed, and so far, the picture has not resolved. Then the next generation arrives. The European Space Agency's Ariel mission is scheduled to launch in 2029, built specifically to survey exoplanet atmospheres by the thousand, rather than one at a time. On the ground, the extremely large telescope in Chile, a single mirror 39 meters across, is expected to see first light around the end of this decade, with the ability to hunt for these molecules using an entirely different technique. And beyond that, NASA's proposed Habitable Worlds Observatory, aimed at imaging Earth-sized planets directly rather than reading their shadows. That one is a project for the 2040s. If it flies, most of the people who will use it are in school right now. Notice the shape of that timeline. The question raised in April 2025 will not be closed in 2025. It may not be closed this decade. The instruments capable of settling it either have not launched or have not been built. That is normal, and it is worth saying plainly, because it runs directly against the way this gets reported. Announcements arrive in a single afternoon. Resolution takes 20 years. Here is the part worth sitting with. K2-18b will keep orbiting through all of it. 33 days. Then 33 more. It has been doing that for billions of years, and it will keep doing it long after every instrument in this list has been switched off. Whatever is or is not in that atmosphere is already true. It has been true the entire time. The only thing that changes is us. So what does all of this actually add up to? Not a discovery of life, not close. What we have is a 3 sigma feature in the spectrum of a planet 124 light-years away, which several independent teams cannot reproduce, caused by a molecule that comets also make. That sounds like a letdown. It is the opposite, because 10 years ago, the honest answer to, is there anything in the atmosphere of a habitable zone planet, was that we had no idea and no way to find out. Now the argument is about which statistical method to use on a real spectrum from a real planet with a real name. The disagreement itself is the achievement. It is the first time in history that a specific, testable, potential biosignature on a specific planet has been argued over in public with real data on the table. 30 years ago, there was no data to argue about, and K2-18b is one planet. Current estimates put the number of planets in our galaxy alone in the hundreds of billions. Sub-Neptunes like this one appear to be the most common kind of all, and this is the first one we have looked at this closely. One planet, 33 days, 3 sigma. That is where the edge of human knowledge currently sits. It is genuinely worth wondering what the other hundreds of billions might be hiding too. If you want more of these, subscribe and turn on notifications. Everything on this channel is grounded in real published research rather than exaggerated headlines.